Okay, so let's continue with the last handful of examples. So again, I would like for you guys for the remainder of the examples to like pause the video and try working them out on your own. Okay, and then you can unpause and then check and see how they are completed. So again, that's going to be important for you guys just to like develop your ability to like critical think and problem solve and not have to see examples worked out for you to be able to work them out on your own. Okay, so I try to do a lot of that in class to help you guys like be able to apply what you've learned to different types of problems. Okay, so with 6, if we try using direct substitution right off the bat, we get rad 1 minus 1, which makes the numerator 0. And when we plug 0 in the place of b in the denominator, that's 0 as well. So that limit is of the form 0 over 0. Not a valid output, but it does tell me that I can somehow manipulate this to eventually be able to use direct substitution. And the technique that's going to work best for you here is multiplying the numerator and denominator by a conjugate. This time we're going to multiply the numerator and denominator by the conjugate of the numerator. Okay, so this is going to become the limit as b approaches 0. Again, we have to keep writing the limit as b approaches 0 until we actually plug 0 into our function. Okay, so again, when we look at that numerator, it is of the form a minus b times a plus b. So that's going to multiply out to a squared minus b squared. So our a value is rad 1 plus b. When I square that, that is going to be 1 plus b minus b squared, which is 1. 1 squared is going to be equal to 1. And then I'm going to leave that denominator in factored form. Because again, we want to ultimately like eliminate factors. So we get the limit as b approaches 0. The numerator becomes b. The denominator is b times rad 1 plus b minus 1. Or sorry, rad 1 plus b plus 1. I made a mistake in the first step. So that should be rad 1 plus b plus 1. Okay, and once we eliminate that common factor in the numerator and denominator, that was the factor that made both the numerator and denominator 0. So once we eliminate that factor, we can now use direct substitution. So this becomes 1 over rad 1 plus b plus 1. And when we plug 0 in the place of b, we get 1 over 1 plus 1, which is 1/2. Okay, so that is the value of our limit, and this limit tells us that there is going to be a hole at the point 0, 1/2. Okay, when we look at 7, we have the limit as h approaches 0 of 5 plus h to the negative 1 power minus 5 to the negative 1 power all over h. Okay, so if I try using direct substitution, plug 0 in the place of h, we get 5 to the negative 1 minus 5 to the negative 1 power, which makes the numerator 0. And then when I plug 0 into the denominator for h, that makes the denominator 0. So again, that's of the form 0 over 0. Not a valid output, but it means that I can use one of the 3 techniques to manipulate that function. I don't think factoring works here. I'm not a fan of the conjugate here either. I actually think the best technique for this one is to simplify our expression. Okay, so this is going to become then the limit as h goes to 0. So 5 plus h to the negative 1 power, that's going to be like the reciprocal of 5 plus h. So that's 1 over 5 plus h minus 5 to the negative 1 power is 1 over 5. And then we are dividing that by h. Okay, so we have a lot of practice with this. Like we have a complex rational expression here. If we want to simplify this, the best way to do so is to figure out the common denominator of your smaller fractions. which is going to be 5 times 5 plus h. And then you're going to multiply the numerator and denominator by that common denominator. Okay, so when we do that, that gives us the limit as h goes to 0. So when I multiply this times the first fraction, the 5 plus h's cancel, so that leaves us with 5, minus, when I multiply this by the second fraction, the 5's cancel, so that leaves us with the quantity 5 plus h. You have to make sure you subtract that entire quantity. Okay, and then on bottom, again, I'm going to keep that denominator in factored form because ultimately I'm going to want to cancel a factor in the numerator and denominator. Okay, so when I distribute the negative in the numerator, we get the limit as h goes to 0 of 5 minus h all over 5h times 5 plus h. And sorry, I'm running out of space, so I'm going to continue the limit on the right-hand side. So this is going to be equal to the limit as h goes to 0. That numerator is going to simplify to negative h. That denominator is 5h times 5 plus h. And then now we can cancel that factor of h on top with the factor of h on bottom. And that was the factor that made both the numerator and denominator 0. So once I get rid of that factor, I can now use direct substitution. So this becomes the limit as h goes to 0 of negative 1 over 5 times 5 plus h. And when I plug 0 in the place of h, we get negative 1 over 5 times 5, which is negative 1 over 25. Again, telling us that there is a hole at the point 0, negative 1 over 25. Okay, I'm not going to write like the whole anymore. We've done enough examples for you to know, like, when you evaluate a limit like this, that there's going to be a hole. Okay, for 8, we have the limit as h approaches 0 of 5 plus h quantity squared minus 25 all over h. So again, if I try using direct substitution, we get 5 squared, which is 25, minus 25, the numerator is 0, over the denominator of 0. Okay, so again, we can utilize one of the 3 techniques here. If I were to guess the way most of you guys would work this out, I would think that you would try to simplify. So when you multiply out 5 plus h squared, that's going to be 25 plus 10h plus h squared minus 25 all over h. So the 25 and negative 25 cancel. And then when you look at the numerator, we can factor an h out of the numerator, which is going to leave me with 10 plus h all over h. And then once we get rid of that factor of h, we can now use direct substitution, and 10 plus 0 makes that limit there equal to 10. And that technique works perfectly fine. Honestly, if I were working it through, that's probably how I would do it as well. Let me show you another one that might not be apparent at first glance. You can actually, if you look at the numerator, that numerator is the difference of 2 squares, because you can write 25 as 5 squared. So if you factor the numerator as the difference of 2 squares, so a squared minus b squared factors to a plus b, which is 5 plus h plus 5, times a minus b, which is 5 plus h minus 5, all over h. If you simplify each of the quantities inside the parentheses, then the numerator is going to give you 10 plus h. The second factor in the numerator is just going to be h all over h. And then you can cancel those factors of h and then use direct substitution. And again, you get that limit to be equal to 10. So there are times where you can utilize more than one of the three techniques. So factoring can work, the conjugate can work, simplifying can work, or more than one of those three can work for your given example. All right, try number 9. Number 9 is a little tricky. So for number 9, you have the limit as x approaches 0 of the absolute value of x divided by x. All right, so let's take a look at what makes 9 tricky. What makes 9 tricky is the absolute value function in the numerator. And the reason that it's tricky is when we take the limit as x approaches 0, depending on what side we take that limit from, that's going to affect how we treat the absolute value function. If you guys remember, we define the absolute value function as a piecewise function. We define it as negative x when the x values are less than 0. We define it as 0 when the x values are equal to 0. And we define it as x when the x values are greater than 0. So depending on what side I take the limit on, whether I take the limit as x approaches 0 from the left-hand side, or I take the limit as x approaches 0 from the right-hand side, that's going to affect the absolute value function and how we rewrite it. Okay, so if we take the limit as x approaches 0 from the left-hand side, we are considering values of x that are less than 0. So we can rewrite the function in the numerator. We can rewrite the absolute value function in the numerator as negative x. So that's negative x divided by x, which is going to give us the limit as x approaches 0 from the left-hand side to be equal to negative 1. And there's nowhere for me to plug that limit in. So that limit is just going to be equal to negative 1. Okay, now when we take the limit as x approaches 0 from the right-hand side, again, because we're taking the limit as x approaches 0 from the right-hand side, that's going to dictate how I write the absolute value function in the numerator. So the absolute value function in the numerator, if our x values are bigger than 0, I'm going to write the absolute value function in the numerator as x. And then x divided by x is 1. So when we take the limit as x approaches 0 from the right-hand side of 1, that limit is equal to 1. And since the limit as x approaches 0 from the left of this function does not equal the limit as x approaches 0 from the right of this function, that limit does not exist. If you were to look at this function graphically, so the absolute value of x divided by x, graphically that function would look like this. So to the left of the y-axis, you would have a hole at the point 0, 1. And then it's going to be the horizontal segment, y is equal to negative 1 extending to the left. And then when the x values are bigger than 0, you're going to have a hole at the point 0, 1. And your line is going to extend to the right. Okay, And when we see the left and right hand limits, those two limits are not the same. Therefore, that limit is not going to exist. Okay, last example, or last thing for us to talk about, and then we're going to do a quick example with this, is called the squeeze theorem or the sandwich theorem. Okay, so I call it the squeeze theorem. Most books call it the squeeze theorem, but some books call it the sandwich theorem. So it says that if f of x is less than or equal to g of x, which is less than or equal to h of x, and the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, and those two limits are equal to L, then the limit as x approaches a of g of x has to be equal to L as well. Okay, so again, if f of x is less than or equal to g of x, which is less than or equal to h of x, and both the limit as x approaches a of f of x and the limit as x approaches a of h of x are equal to L, then the limit as x approaches a of g of x has to be equal to L as well. And again, I had to fix my drawing because I labeled the functions wrong. Okay, but they're correct now. Okay, so what this is saying is that if your function g of x is between f of x and h of x, and when you take the limit as x approaches a of the smaller function and the limit as x approaches a of the larger function, and those two limits go to L, then that squeezes or sandwiches the limit as x approaches a of g of x, and it forces that limit to be equal to L as well. All right, so I'm going to do just one quick example with this. So it says, given the function 4x minus 9 is less than or equal to f of x, which is less than or equal to x squared minus 4x plus 7, then we're asked to find the limit as x approaches 4 of f of x. Okay, so we have our function f of x that is bounded in between two other functions. Okay, 4x minus 9 and x squared minus 4x plus 7. Okay, so if you have a compound inequality like this and you want to apply the limit as x approaches 4 to f of x, we're going to take the limit as x approaches 4 of each of these functions. Okay, so we're going to take the limit as x approaches 4 of 4x minus 9. That has to be equal to the limit as x approaches 4 of f of x, which has to be less than or equal to the limit as x approaches 4 of x squared minus 4x plus 7. Okay, so if I want to evaluate the first limit, I can do that with direct substitution. So when I plug 4 in the place of x, we get 4 times 4, which is 16, minus 9, which is equal to 7. Okay, now I can do the same thing with the last limit. The limit as x approaches 4 of x squared minus 4x plus 7. Okay, so when I plug 4 in the place of x, we get 4 squared, which is 16, minus 4 times 4, which is 16. So 16 minus 16 is 0. 0 plus 7 makes that limit equal to 7 as well. And if both of those limits are equal to 7, then that forces the limit as x approaches 4 of f of x to be equal to 7 as well. Okay, utilizing the squeeze theorem. Okay, so that's going to wrap up this lesson on verifying limits analytically, and we'll see you guys in class on Monday. Take care.